Hello, this is our Chem 113 video lab report. I'm Dr. Proctor, subbing for Dr. Mullins today.
I'm Levi Crossley.
And I'm Gabby Jackson.
And so this is our video lab report for experiment 3, determination of a chemical formula. So, let's get to it, class. So first off, introduction-wise, what we need to know. Elements combine in fixed ratios to form compounds. So, for example, some technical difficulties will go around them though. So, for example, if you look at the compound AlCl3, which is class chloride, yes, good job, aluminum chloride. Each molecule of aluminum chloride is composed of exactly one aluminum atom and 3 chloride atoms, which you learn from the subscripts, right? Are you following me? You following me? So, look, as we continue, a mole. What is a mole? It's a unit. What is that unit? It could represent the amount of molecules, the amount of ions, the amount of atoms. It could represent anything. By definition, the mole is the number of atoms in a thing. Pretty much. Which is 6.02 times 10 to the 23rd. Good job. You get brownie points. This is called what number, Levi? Whose number is that?
Avogadro's number.
Avogadro's number. We're just doing real good. That didn't work right. Still didn't work right. But we'll be alright because we have to use this. 1 mole of aluminum with 3 moles of chlorine produces how many moles of aluminum chloride? Based on this right here. You have 1 mole of aluminum and 3 moles of chlorine. How many moles of aluminum chloride do you have? You have 1 mole of aluminum chloride. This is all 1 mole. And because of the dead Latin dudes, that's how you write mole in chemistry. So, 1 mole of aluminum with 3 moles of chlorine combines to produce 1 mole of aluminum chloride. So the molar ratio of aluminum to chlorine is 1 to 3. Ignore all that right now. And so, what is that? If you divided 1 by 3, what do you get? 0.33, 0.33. That's right. And so, if you think about it the other way, what is the molar ratio for chlorine to aluminum? 3. That's good. 3.0. So, if you don't know the formula of a particular compound, you might think that you're up a creek without a paddle. Right, Gabby?
Yeah.
You might think you're up a creek without a paddle. But if you know the molar ratio of 2 elements, in the compound, you can use that ratio to determine the simplest possible formula for the compound, which is what we're going to talk about today and do in the lab, the empirical formula. Okay, so to determine an empirical formula, which you all will have to do today in the lab, we're going to say that we determine a ratio for a lab that is composed of nitrogen and hydrogen. Not together. Nitrogen and hydrogen. It wants to change colors, but we'll work with that in chemistry. So if we want to look at the moles of hydrogen in a sample in the compound, we see that it is 0.2, I lied, 0.0299 moles. Okay? And then if we look at the moles of nitrogen below that, it is 0.0100. Are you following me, class? Okay.
Yes.
So, Mr. Crossley, could you come up here and compute that for us? Or just use your head. Go ahead, show us how you do that.
Okay, so you would divide this by this, and that's going to get
2.99.
which is about 3 over 1.
So a 3 to 1
Which is-
ratio.
3.
3 to 1 ratio. That's good. That's good. That's a good job, Mr. Crossley. I appreciate that hard work and effort by you. But as we talked about inversely, we could also put nitrogen, not in, but nitrogen on top with 0.0100 over hydrogen, and that being 0.0299, and you would have a 1:3 ratio for your molar ratio. That's also 0.334-ish. Approximately. Are you all following me still? Are you awake?
Wide awake.
Wide awake?
Wide awake.
That's good. Chemistry's fun, right? Because we get to blow stuff up. Right? Sometimes. So from either of these ratios, if you either look at hydrogen over nitrogen or nitrogen over hydrogen, you know that there are approximately 3 hydrogens for every nitrogen, correct?
Correct.
That's what you see because there's 3 to 1. That's your ratio. 3 hydrogens, 3 nitrogens, 1. Those units don't leave. That's still hydrogen, that's still nitrogen. Okay? So the simplest possible formula for the compound would be what, Ms. Jackson? Could you come up here and demonstrate the simplest possible formula? The simplest possible formula of the compound would be, let me get my water. Explain to us how you got that, Ms. Jackson.
Because there's one nitrogen for every other ally. Because you have to do a little swapping and swapping, so because there's
3 hydrogens for every 1 nitrogen. Good job. So there's 2 parts to this experiment that you all are going to do today. In part A, you will determine the chemical formula of a compound that is composed of only zinc and iron. What's the chemical equation or symbol for zinc?
Zn.
Zn. And for
I think maybe you're highlighting. Oh my
iodine? Iodine?
Ah.
Incorrect. I2. Why I2? Because it is a diatomic element, Mr. Crossley. You must always remember that.
Misunderstood the question.
Now, you will not know the exact experimental formula of this compound ahead of time. It is an unknown. But you will be able to determine its chemical formula by determining the number of moles of zinc that combine with the given number of moles of iodine. You'll also calculate the number of moles and iodine from the masses of gram of zinc and iodine in the compound. You'll also use this same strategy in part B to determine the number of moles of water in a hydrate, and along with the determination of the identity of an anhydrous metal salt produced. You will determine the formula of the unknown hydrate compound. And so, as we're about to begin the experiment, I looked through your all's pre-labs today, and as I was typing over here, I used a very excellent example of a pre-lab procedure, or purpose, not procedure, purpose. They both start with a P, as well as Dr. Proctor. But, so, Ms. Jackson, I used your purpose statement. Could you come up here and just explain to us a little bit about your purpose statement? Read it to us and talk about it.
So my purpose statement was that the purpose of this lab is to synthesize and determine the empirical formula of the product of reaction of zinc metal with a solid iodine to determine the formula of an unknown hydrate. So basically, what we're going to do is we're going to mix some zinc with some other stuff to find the unknown hydrate.
Very good. Thank you. So, that is the purpose of this lab. Need some dihydrogen monoxide, I'm sorry. Which is a what type of bond? Covalent. Covered in there. And so we're going to go ahead and we're going to get started with the materials today. Because even though we're not in the lab at this moment, you all have already conducted this experiment. We're discussing it. And so I used Mr. Crossley's excellent list of materials. So could you just run through the materials for us up here, Mr. Crossley?
Okay. So you have to use a 50 milliliter or 100 milliliter beaker. You're going to use a Bunsen burner.
And that Bunsen burner was replacing a hot plate, correct?
Correct.
Okay.
And the unknown hydrate, which is what you'll be adding to the zinc metal, iodine, and 2 m of acidic
What
acid.
is 0.2 m mean?
2 molecular.
Ms. Jackson, do you know what 0.2 m means?
2 moles of acetic acid.
Not 2 moles. Keep going. I'll explain that in just a minute.
Okay, thank you. A crucible and the cover, an iron ring, and stand, and a wire gauze.
Okay. Thank you. So, if you could please turn your cell phones off in the classroom. That would be helpful. It would also be helpful if technology cooperated. But there we go. So, 0.2 m, capital M, of acetic acid. I believe you all went over this in lecture. You may just have forgotten. That is 0.2 molar acetic acid, which means that the ratio is 0.2 per molar, and that is equal to moles over liters. It tells you how many moles per liter. So in this case, that is always usually going to be over 1 liter. So you've got, for every liter of water, you have 0.2 moles of acetic acid. Does that make sense?
Yes.
Okay. So, 0.2 moles of acetic acid for every 1 liter of what you're diluting it in. So, we're going to go ahead and we're going to get started. Today with you all explaining what you all did on your lab. We're going to go ahead and start with the procedure. I've got my lab manual. Thank you, Mr. Crossley. And so everywhere that there's some calculations, I may jump in or anything that's going on. So we'll go ahead and get started today. There, with the procedure, and we'll start with RNA. So, who would like to come up first and give us just a few points of the procedure for part A? Mr. Crossley, would you like to come up here and just, give us a few of the first points of part A?
Okay, so this is the zinc iodine, and you're going to weigh your 50 or 100 meter beaker, and you're going to record the mass as accurately as possible.
What was your mass, sir?
The mass,
I'll go with my own calculations. As you explain, I'll go with my own calculations. That's how we'll do it.
right.
So I used a 50 milliliter beaker, and that weighed 29.07 grams. So, continue, please, sir.
Okay. Then you're going to remove the beaker from the balance and add approximately 0.6 grams of metallic zinc into the beaker, and then you're going to place that back on the balance to weigh it.
Okay, did you just, put the 0.6 grams on there randomly, or did you use some weight paper?
I use the weigh paper.
Weight paper. And so, our weight paper, you have to take that into consideration, weighed 0.4 grams. Are you also on the same page with this, Ms. Jackson? Okay. So, you weighed out 0.6 grams of metallic zinc.
Right.
And how close were you to 0.6 grams? Were you right on 0.6? Or were you a little bit off? Just a little bit off?
I was slightly off.
Okay, because I believe you are got 0.66 grams for the zinc, correct?
Correct.
Okay. And therefore, that's how that went, correct?
Correct.
And what did you all weigh out for iodine? How much did you weigh on that? You were a little closer on that, correct?
We're going on your numbers, so yeah, I was close.
Okay, so you got this 0.66 grams
Right.
for zinc, and then you said that your iodine was a little bit closer. I looked at your sheet, and for your iodine, was it that you had 0.61 grams?
Correct.
0.61 grams. And so that adds up for your total weight of the beaker and the zinc and the iodine to be 30.33 grams, correct? That's what you said you had?
Correct.
Okay. So, did you copy all this down, Ms. Jackson? Or did you have it already?
Already had it.
You already have it, okay. Well, if everybody, class, does everybody have that copy down? So, Ms. Jackson, you're up here to help us a little bit more. What step are you starting on?
Number 4.
Step 4. And what did you have there?
You're going to add approximately 5 milliliters to the beaker of 0.2.
5 mils to the beaker of 0.2 acetic acid, correct?
Yes. Of acetic acid.
14 molars, see? I did that on purpose to test them, see if they would remember about molarity, which we discussed beforehand. That's a lie, forgive me, Jesus. Acetic acid. So, you added that in, and as you did that, what were you doing with the beaker? You were
Yeah, you were spinning it.
swirling.
But that's not all step 4.
Okay, and what else is in step 4?
It says the acetic acid provides a medium for the action to occur in, as well as preventing the undesirable precipitation of ZnOH2.
Of what?
ZnOH2.
That doesn't make any sense. What is ZnOH2?
Zinc
Zinc hydroxide, Ms. Jackson. That's what you were referring to when you said ZnOH2, correct?
Yes.
Okay, so you all poured. We'll discuss this real quick. You all poured in this 5 mils of acetic acid in at 240, correct?
Yes.
240 p.m. Okay? And so, how long was this experiment supposed to take, or this process supposed to take?
It's supposed to take about 30 minutes.
About 20 minutes,
20 minutes.
according to your lab sheet. You may have written 30, but that would be incorrect. So, you all waited 30 minutes, and at 3:10 p.m., what did you all do? Could you please tell me? You added how many more milliliters?
5 more milliliters.
5 milliliters more added.
And when we started, it was a reddish color after that.
Oh, Okay, we can add that. So good observations. That's good skills right there. Red. At that time. Oh, do you remember what color it was at this time?
It was the same color, it was just more diluted.
So also red. And so at you all waited another 31 minutes. You said that's awful specific. I don't know why anyone would get that specific. I'm just kidding. This is chemistry. We are specific. What? How much more did you add then?
2.7 milliliters.
2.7 more milliliters was added. Color still the same?
Yeah, just diluted more.
Okay. And what time did you call the experiment or call this process?
At 3:58
p.m. So it sat there for a total of an hour and 18 minutes and did not fully complete like it was supposed to, correct? Okay, so if it had worked like it was supposed to, all of the what was supposed to be gone?
Zinc.
Or not, it's supposed to be gone. But it's supposed to have reacted. What was supposed to have reacted?
The zinc and the unknown hydrogen.
At the end of the 20 minutes, which did not work, all the iodine should have reacted, and the solution should have contained an aqueous, potato, tomato. Same difference in Milo. I am Dr. Proctor. It should have contained an aqueous, zinc, iodine, and acetic acid solution. So, what did you do to that solution? You decanted it. And how did that go? Did that go pretty good?
Sure.
Did it go pretty good?
Yeah.
So you decanted the solution to a clean, dry 100 milliliter beaker, I'm assuming, right?
Yes.
What was the mass of that 100 milliliter beaker?
49.89 grams.
49.89 grams. Are you sure that's what you got?
I'm 100% confident.
You're 100% confident.
Yes.
Okay, so the excess zinc will stay in its original container, correct?
Beaker, but yes.
Beaker container. A beaker is a container. So, thank you, Mr. Jackson. We're going to have Mr. Crossley come back up. I only seem to have 2 interested students today. Nobody else seems to be wanting to participate. What are you scoffing at, Mr. Crossley? I thought you were here to help me.
I'm here to help.
You are?
Oh yeah, I'm here.
You're here? You're here for me?
I'm here for you.
I am proud to call you my student. Still talking about part A. So, Mr. Crossley, you're up here to help us. And what did you do next?
Okay, so I added 3 milliliters of 0.2 molar acetic acid to the beaker with the solid zinc. And then I swirled that for a few times. Then I decanted most of the solution into the product solution beaker. And I was making sure that I left all the solid zinc in it.
You wanted to leave all the solid zinc in its original container?
Correct.
Okay. And so you repeated those steps how many times? 3 times,
3
correct?
times, yes.
Okay. So, times 3.
And next I discarded the acetic acid into the collection beaker. And I washed the solid zinc with 3 times. I washed it 3 times with DI water.
Okay.
And now I took
Okay, hold up. So, does everybody have that written down? Back to this. After you had washed your beaker and done everything that you were told to do, you dried your zinc, right?
Right. And
Using the
hot plate.
But we didn't have a hot plate, so you used a
Bunsen burner.
Bunsen burner. That's good. And you let that cool down, and your post, drying weight was 29.56 grams, correct?
Correct.
And so then you heat it again, and you said that after that cooled, your mass was also the exact same, 29.56, right?
Right.
56 grams. So because of that, you were finished because you were within 0.01 grams.
Correct.
Okay, Miss Jackson, you were also within 0.01 grams. Timmy, were you within 0.01 grams? You were. Timmy was within 0.101 grams. 0.01 grams. So that is the gist of part A of the procedure. So, after part A, what comes after A in the alphabet class?
B. Part B.
B. That was good. We'll switch colors for this. Does anyone like the color red?
Yeah, we got red.
Red's a good color. So, part B, Miss Jackson, you can go ahead and be making your way up to the front, and you'll start us out with part B. Okay? So
part B is for the unknown hydrate.
and your unknown number was, or letter, it is.
C.
You had unknown C. So your unknown was C, and what are the three possibilities for your unknown hydrate?
Magnesium sulfate,
Which is MgSO4, and then plus your hydrate, H2O. And then the next one was?
zinc sulfate, which is CnSO4, and your hydrate. Or strontium chloride, which is
SrCl. H2. Oh, correct.
Yeah. Then you're gonna weigh clean dry crucible, and the crucible lid was 45.74 grams.
It was how much, Ryan?
45.74 grams.
So we're going to write C up at the top so we remember it. And so crucible and cover weighed 45.74 grams.
Yeah.
Okay.
Then after you do that, you're gonna add 4 grams of your unknown hydrate, so of C, and you're gonna place that back on the balance and record the mass of the hydrate.
And how much was that?
But you didn't just put it with the crucible; you had to put it in a weight boat.
That's true.
Weight boat weighed 13.47 grams, and with the unknown, it was 14.02 grams.
Okay, so, but you all didn't use 4 grams of the unknown? No, you didn't. You might not remember because we did the experiment 3 so long ago. But there was such a small amount, if you'll remember, class. Timmy, paying attention? Timmy, okay. Timmy's on board. There was such a small amount of unknown available that we decided that we would use, around half a gram. So you said you used 0.55 grams of unknown?
Yes.
Correct?
Yeah.
Okay.
And
So,
put it with the crucible. Place the crucible and the unknown in it. You weighed it.
and you
Weighed
did what?
46.32 grams, which means the unknown weighed 0.58 grams.
So your original measure was 0.55, but it was 0.58.
Yes.
So that's crucible and unknown.
And after that, we place the crucible with the unknown in the Bunsen burner because you didn't have a hot plate.
And you heated it, correct?
Yes, but you didn't put the lid all the way on there securely. You left it kind of ajar.
Is there a reason for that?
So that the stuff can escape.
That's true. So you started heating at
254.
2:54 p.m. and first heating, what was the mass?
46.06 grams.
46.06 grams. So you went back,
We heated it again.
heated it again.
After that, there's a
You heated at 329.
After that, it was 46.05.
Mass
Since-
was 46.05. And since what were you saying?
Since it was within 0.01, we were done heating.
You were finished heating.
Yes.
Okay. And so, now, Mr. Crossley, could you come up here just real quick and discuss the very end of that experiment with us? So the mass is within 0.01 grams. And so you poured a small portion of what's that big M mean? Molar hydrochloric acid aqueous solution into a small beaker, correct?
Correct.
And then what did you do?
And then I lit my Bunsen burner and took a metal spatula and I cleaned it by dipping it into that solution right here.
Okay.
And then
You place some of your unknown on the spatula, right?
right,
And this was to test which unknown it was, right?
correct.
And if you saw a bright red flame, you had strontium chloride. Did you see a bright red flame?
No.
No bright red flame. So strontium chloride is out. So if you have the red flame, you put about 1/10 of a gram of the unknown into a test tube. And you added a few milliliters of ionized water. Then you drop some magnesium and wait approximately 5 minutes. If the magnesium was collecting on the strip, it was magnesium sulfate. Did yours collect on it? It did not. So it wasn't magnesium sulfate. So your unknown C was zinc sulfate. Correct?
Correct.
Thank you very much, sir. So we will move on and get to the calculations now. Okay, so on to the calculations now for part A. You see this? So it's basically plug and chug. I gave you all in the lab handout what to plug in. So we're just going to run through this real quick. Moles of I. Now notice it's I, not I2. So that is equal to the moles of I weighed massed, which was 0.61 grams over the atomic mass, or the molar mass of I. And that is 126.9 grams per mole. And so that gave you 0.0048 moles of I. Correct? Item. Is that what you all got? Right. So then when you looked at moles of zinc, you had 0.17 grams of zinc that was reacted over but 65.38 grams per mole, which is the molar mass of zinc. And so you do that, and that equals 0.0026 grams, moles of zinc. And so what you do is you react to find this number, because I put 0.17 up here without really telling you all how to get it. But I think you all have this in your calculations, right? What you do to find that is some more plug and chug. Did everybody have that? Timmy, did you have that? Timmy. Good job. I'm proud. You took your reacted zinc, which would be your points, or to find your reacted zinc, 0.66 grams, which was your original amount of zinc, minus 0.49 grams of zinc, which is what you had remaining. So that gave you your 0.17 grams of zinc. Okay? So what you do is now you have 0.0048 moles of I. You have 0.002. I'm sorry. I'm sorry. I did not learn how to write today. 0.0026 moles of zinc, and you divide those numbers, which gives you a molar ratio, which we talked about earlier, of 2 to 1, right? So that is around 1.8, but your number N is going to be equal to 2. Therefore, your chemical equation is Zn, or your empirical formula is Zn to I. Is that what everybody got?
Yes.
It is. That's good. So, we can move on now to the calculations in part B. I know I'm kind of rushing through this, Timmy, but I think that everybody had their calculations down right to begin with. So, to find the mass of the water you use, you took the mass of your hydrate, subtracted from the mass of the salt, which gave you the mass of the water. Okay? Is everybody following me? To find the mass of the salt, you took your crucible with salt after the last heating, minus the crucible, which added up to me. We're going to go ahead and find salt first. That was 0.58 grams. And you took that from the molar mass of salt being NaCl, right?
Right.
And the molar mass was, you have that right there, don't you, man? Yeah, right there. 161.44 grams. And so that gives you 0.0036 moles of salt. Now below that, you have moles of water. You have 0.27 grams of water, or the molar mass of water, which we all know to be 18.02 grams per mole. And that gives you 0.015 moles of water. Y'all following me still? Okay. We're about done with our calculations. And then we'll move on to a good little conclusion. And I'll let you all go. I think you should get out a little bit earlier. We're not going to use the full 3-hour period. So, you take those numbers. We're going to flip from what I did. We're going to do water first, just for my sake. And we had 0.015 moles of water. Salt down below. That gives you 0.0036 moles. X, which is what you put out in front of your H2O, was 4.17. Because you've got 4 over 1, basically. You know, we rounded a little bit. So you have 4 H2O here. You understand that? We're all on the same page? Your actual number was, I think, 4.17, but like I said, we round. Timmy, did you have that? Okay. Yeah. And now conclusion. Mr. Crossley, could you read us our conclusion? Then we'll just briefly discuss it. Oh, I'm sorry, I'm a failure.
Okay, so the empirical formula of zinc iodine is zinc I2. And some possible sources of error that would have affected the results would be that we had a large amount of acetic acid to the we added a large amount of acetic acid to the solution.
Was that where you all put a bunch more in there because the reaction was taking too long?
Correct. We tried to speed up the reaction process. And then our unknown was zinc sulfate, and the unknown number was 4, and the formula of the hydrate is salt times 4 molecules of H2O. And some possible sources of error could be that we didn't weigh the solution correctly, which would give us incorrect empirical formula for our hydrate.
Anything you'd like to add to that, Miss Jackson? You think that was good? Covered everything good? Okay, so we'll just end this class period. Miss Jackson, what were some of the references you had?
One of the references that I had was the chemistry book.
Chemistry textbook. You also had the lab handout and, notes that you want to put in lab. Those are all things that we could use in order to help us understand this lab better. Does anybody have any questions? Okay, well, that's very good. Thank you all. You are dismissed, class.